In September 1944, a F6F Hellcat from USS Hornet suffered engine failure while attacking targets in Norway and force-landed near Trondheim, falling intact into German hands before its pilot could destroy the aircraft. For German engineers who had spent years designing fighters for land-based operations where every pound mattered and carrier-based fighters were assumed to be performance-compromised designs suitable only for naval defense, this captured American naval fighter represented something they could barely comprehend. An aircraft burdened with folding wings, arresting gear, reinforced structure for carrier landings, and all the weight penalties of naval aviation that nevertheless achieved 380 miles per hour at 20,500 feet in level flight, faster than the Bf-109G6 at the same altitude, competitive with the FW-190A8, and faster than any German fighter operating at that specific altitude in standard combat configuration. What these engineers would discover during their evaluation would force them to confront an uncomfortable reality about the divergence between German and American engineering philosophy, that while German designers obsessed over removing every unnecessary gram to optimize performance for land operations, American engineers had built a carrier fighter with folding wings and arrestor hooks that could still outperform German land-based fighters at medium altitudes, achieving this seemingly impossible combination through brute force engineering with a 2,000 horsepower radial engine and two-stage supercharger that maintained power where German engines gasped. This is the story of how German engineers learned that American industrial capacity had reached the point where even weight penalized. Naval fighters outperformed German fighters optimized for weight reduction, and how honest technical reports documenting this capability gap traveled through a command structure that had neither the resources to respond nor the philosophical framework to accept that carrier. Aviation had achieved performance parity with land-based aviation. Subscribe now for the untold engineering stories of World War II, where German engineers testing captured Allied aircraft discovered that American naval fighters designed for carrier operations with all their inherent weight penalties could still match or exceed German land-based fighters optimized for minimum weight, where two-stage superchargers and massive radial engines overcame structural disadvantages through sheer power, and where the technical reports documenting American superiority gathered dust in filing cabinets while the war was lost. We reveal the engineering reality that determined outcomes. Hit subscribe. September 19th, 1944. Vernes Airfield, Trondheim, Norway. The morning is cold and damp. Autumn asserting itself on the Norwegian coast with temperatures barely above 10 degrees Celsius. Steady rain falling from low gray clouds that touch the mountains surrounding the fjord. Visibility poor but adequate for the technical evaluation that is about to begin. Oberingenieur Hermann Wurster stands beside a sandbagged revetment, collar of his leather coat turned up against the rain, studying the aircraft before him with an expression that transitions from professional curiosity to genuine confusion as he processes what he is seeing. The Grumman F6F Hellcat Bureau number 58312 sits on German concrete, looking impossibly large and brutish. Its dark navy blue paint scheme still bearing the white stars of the U.S. Navy. Its wings folded upward in the characteristic carrier storage configuration that makes the fighter look like a massive metal bird with wings raised in surrender, its radial engine cowling huge and purposeful, its entire presence speaking of design philosophy fundamentally different from German fighter practice. The aircraft was captured 3 days ago when its pilot, Lieutenant Junior Grade Thomas Riley from Massachusetts, suffered complete engine failure while his squadron attacked German shipping in Trondheim Fjord and was forced to ditch in shallow water near the shoreline. German troops reached the aircraft before it sank completely, before Riley could set demolition charges, and within hours the Hellcat was being hauled from the water and transported to Vernes, where the Luftwaffe maintains a technical evaluation facility primarily for analyzing captured Soviet aircraft but equipped to handle any enemy fighter that falls into German hands. Wurster is 42 years old, a civilian engineer employed by Focke-Wulf, assigned to Norway temporarily to evaluate captured Allied aircraft and provide technical intelligence for German fighter development programs. He holds a doctorate in aeronautical engineering from Technical University Berlin, has worked on fighter design since 1936, contributed to the FW-190 development program, and brings systematic engineering perspective to aircraft evaluation rather than just pilot impressions. He is here because the Hellcat represents a type of aircraft German engineers barely understand. A carrier-based naval fighter designed from the beginning to operate from aircraft carriers, accepting all the weight penalties and structural compromises that carrier operations demand, yet reportedly achieving performance comparable to land-based fighters that have none of these constraints. German naval aviation is virtually non-existent by September 1944. The carrier Graf Zeppelin never completed. German fighter pilots have no experience with carrier operations, and German engineers have no practical knowledge of how to design aircraft for carrier use. The Hellcat is an opportunity to understand how American engineers solve problems German engineers never seriously attempted to solve, how they overcame weight penalties that German design philosophy assumes are insurmountable, and most troublingly, how they built a naval fighter that, by all German engineering assumptions, should be slow and performance compromised, but instead achieves speeds German land-based fighters struggle to match. The immediate visual impression the Hellcat creates is mass. Everything about the aircraft is substantial, heavy, overbuilt by German standards. The fuselage is deep and wide, accommodating the massive Pratt & Whitney R2800 double Wasp radial engine. 18 cylinders arranged in 2 rows, producing 2,000 horsepower. German radial engine fighters like the FW-190 use 14-cylinder radials, producing 1,600 to 1,700 horsepower. The American engine is larger, heavier, more powerful, representing brute force approach to achieving performance. The wings are thick at the root, structurally reinforced to withstand catapult launches and arrested landings that subject the airframe to forces land-based fighters never experience. The landing gear is massively built. Heavy struts designed to absorb carrier landing impacts at sink rates that would destroy landing gear on German fighters designed only for land operations. Most strikingly, the wings fold at mid-span, hydraulic mechanisms allowing the outer wing panels to rotate upward for compact carrier storage, adding weight and complexity that German fighters eliminate by using fixed wings. Every aspect of the Hellcat's design incorporates features required for carrier operations. Features that add weight, reduce performance, create complexity. Features that German engineering philosophy would eliminate to optimize fighter performance. Yet, according to captured American technical documentation and pilot interrogation reports, this weight-penalized carrier fighter achieves maximum speed of 380 miles per hour at 20,500 feet. Worcester knows these numbers from intelligence summaries, but initially assumed they were exaggerated. Propaganda figures inflated to improve American pilot morale or to deceive German intelligence. But preliminary examination of the Hellcat's structure and system suggests the performance. Figures might actually be accurate, that American engineers might have actually built a carrier fighter that matches German land-based fighter performance despite carrying hundreds of pounds of additional weight for naval features. If this is true, if the Hellcat really achieves 380 miles per hour at 20,000 feet while carrying folding wings and arrestor gear, then German engineering assumptions about the relationship between weight and performance are fundamentally wrong. And American industrial capacity has reached the point where they can simply overwhelm weight penalties through massive engines and sophisticated supercharging. Behind Worcester, 3 other specialists wait in the Norwegian rain, all experts in their respective fields selected for this evaluation because the Hellcat represents technical challenges requiring multidisciplinary analysis. Hauptmann Heinz Bauer, 30 years old with 220 confirmed victories, one of the Luftwaffe's most experienced test pilots who flew evaluation flights on dozens of captured Allied aircraft and brings combat perspective to technical assessment. Oberins Franz Zeidel, 38 years old, supercharger specialist from Daimler-Benz who understands the thermodynamic principles that determine high-altitude performance and who will analyze the Hellcat's 2-stage supercharger system, and engineer Karl Hoffmann, 35 years old, structural engineer from Messerschmitt, who will examine how the Hellcat's structure achieves strength adequate for carrier operations without becoming so heavy that performance becomes unacceptable. These 4 men collectively represent hundreds of hours of fighter design experience, decades of aeronautical engineering knowledge, and growing awareness that American aircraft development has progressed to the point where German fighters are being systematically outclassed, despite German engineers' best efforts. The Hellcat has been made airworthy in 3 days of intensive work by Luftwaffe mechanics who were simultaneously impressed and intimidated by what they found. The damage from the ditching was moderate. The engine ingested salt water and seized. The propeller was damaged by striking water during the landing. Structural damage to the belly and tail section required repair. The electrical system was shorted by saltwater immersion. Mechanics disassembled the R2800 engine completely, cleaned every component, replaced damaged bearings and seals using improvised parts fabricated from measurements, reassembled carefully and tested extensively before declaring it airworthy. The propeller was replaced using a propeller taken from a crashed American P-47 Thunderbolt, which uses a similar 4-bladed Hamilton standard propeller, modifications required but manageable. The structural damage was repaired using aluminum sheet and rivets, the patches ugly but functional. The electrical system was rebuilt, replacing corroded wiring and water-damaged components. The entire process was complicated by the Hellcat systems being more complex than German fighters, with hydraulic mechanisms for landing gear, wing folding, and flaps, with pneumatic systems for engine starting and emergency operations, with electrical systems that control everything from engine management to weapons to flight instruments. German fighters are simpler, more mechanical, easier to maintain in field conditions, but perhaps less capable as a result. What struck the German mechanics most forcefully during the restoration work was the Hellcat's construction quality and attention to detail. Every component is precisely manufactured, every fit is tight, every surface is smooth, every fastener is properly torqued. The quality control is evident in ways large and small, perfect rivet lines showing no variations. Wiring harnesses with individual wires color-coded and secured neatly. Hydraulic fittings that seal without leaking. Structural joints that show no gaps or misalignment. By contrast, late-war German aircraft increasingly show quality degradation, rivets that do not sit flush, wiring that is hastily installed without proper securing, hydraulic systems that leak and require constant maintenance, structural assembly that shows gaps in misalignment due to rushed production and inadequately trained workers. The Hellcat represents industrial production standards German aviation cannot match in September 1944, when Allied bombing has disrupted manufacturing, when skilled workers have been drafted into military service, when material shortages force use of inferior substitutes, when production pressure demands quantity over quality. The mechanical superiority visible in every component of the Hellcat is as discouraging to German mechanics as its performance specifications are to German engineers. Worcester walks slowly around the Hellcat, his engineer's eye cataloging every detail, taking notes in a rain-dampened notebook, forming preliminary assessments that will be validated or corrected through flight testing and detailed technical analysis. The wings are low-mounted, attached to the fuselage at a point that appears carefully chosen to optimize aerodynamic efficiency while maintaining structural efficiency for the stresses of carrier landings. The wing loading is moderate, approximately 35 pounds per square foot, higher than the Bf-109G's 32 pounds per square foot, but lower than the FW-190A8's 41 pounds per square foot, suggesting the Hellcat will turn adequately, if not brilliantly, will maintain controllability at low speeds needed for carrier approaches, will handle predictably throughout the flight envelope. The folding mechanism is sophisticated, hydraulic actuators rotating the outer wing panels upward 90 degrees, reducing the aircraft's wingspan from 42 feet to 17 feet for carrier storage. The mechanism adds approximately 250 pounds compared to fixed wings. Significant weight penalty, but essential for naval operations where hangar deck space determines how many aircraft a carrier can deploy. German engineers designing land-based fighters never face this constraint and consequently never develop expertise in designing efficient folding mechanisms. The landing gear is exceptionally robust, much heavier than German practice, designed to withstand sink rates of 13 feet per second at touchdown compared to the 6 to 8 feet per second that characterizes normal land-based fighter landings. Carrier landings are essentially controlled crashes, the aircraft striking the deck hard enough to engage the arresting wire, absorbing impact energy that would collapse landing gear designed only for smooth airfield landings. The Hellcat's landing gear uses massive struts with long-stroke oleo dampers, reinforced attachment points distributing loads throughout the wing structure, and wheels with heavily reinforced hubs. The entire landing gear system weighs approximately 500 pounds more than equivalent system for land-based fighter. Major weight penalty, but necessary for survival and carrier operations. The arresting hook is mounted under the tail, a sturdy mechanism weighing approximately 100 pounds that extends downward to engage carrier deck wires. The hook, the reinforced structure to support hook loads during arrested landings. The strengthened tail section, all add weight that land-based fighters do not carry. Worcester estimates the total weight penalty for carrier-specific features, folding wings plus reinforced landing gear plus arresting gear plus strengthened structure, is approximately 800 to 1,000 pounds. The Hellcat weighs this much more than a land-based fighter of similar dimensions would weigh, yet reportedly achieves similar or better performance. The engineering to overcome this weight penalty must be extraordinary. The engine installation reveals how American engineers achieved performance despite weight penalties. The Pratt & Whitney R280010WW Wasp dominates the forward fuselage, a massive radial engine displacing 2,800 cubic inches, 46 liters, producing 2,000 horsepower at takeoff power and 2,200 horsepower at war emergency power with water injection. The engine weighs 2,300 pounds, 400 pounds heavier than the BMW 801D and the FW190A, but produces 300 horsepower more. The power-to-weight ratio of the engine itself is better than German radial engines, suggesting American metallurgy and manufacturing allow higher specific power. More significantly, the R2800 is equipped with a two-stage two-speed supercharger, similar to the system in the Packard Merlin that powers the P-51 Mustang, maintaining power at altitudes where single-stage supercharged German engines lose effectiveness. The supercharger is the key to the Hellcat's altitude performance, allowing the engine to maintain high power output at 20,000 feet where air density is less than half sea level density. German radial engines use single-stage superchargers with critical altitudes around 18,000 feet, above which power drops rapidly. The Hellcat's two-stage system maintains power effectively to 25,000 feet, providing sustained high-altitude performance that German radial fighters cannot match. The cowling design is sophisticated, carefully shaped to minimize drag, while providing adequate cooling airflow for the massive engine. The cowl flaps are adjustable, controlled from the cockpit, allowing the pilot to balance cooling requirements against drag. Opening flaps for maximum cooling during high-power operations or closing them for minimum drag during cruise flight. The exhaust system features individual ejector stacks for each cylinder. 18 exhaust stacks arranged around the cowling, each stack shaped to provide thrust augmentation by directing exhaust gases rearward at high velocity. The exhaust thrust is estimated to provide approximately 150 pounds of additional thrust at high power, equivalent to about 5% increase in effective engine power, demonstrating attention to efficiency that extracts performance from every possible source. German fighters increasingly neglect such details as production pressure prioritizes quantity, accepting performance losses to simplify manufacturing. The Hellcat shows no such compromises, every system optimized for performance even when optimization adds cost and complexity to manufacturing. The cockpit arrangement reveals American priorities for pilot survival and combat effectiveness. Worcester climbs up using handholds and footholds built into the left side of the fuselage. Pulls himself into the cockpit, immediately struck by how spacious it feels compared to German fighters. The canopy is large, providing panoramic visibility. Bubble-style aft section allowing the pilot to see directly behind without blind spots. The seat is comfortable, heavily armored with thick steel plates behind and below, protecting the pilot from rear attacks and ground fire during low-altitude strafing. The armor weighs approximately 230 pounds, comparable to late-war German fighters but heavy compared to early war designs that used minimal or no armor. American experience in combat demonstrated that pilot survival requires armor protection. That losing trained pilots is more costly than accepting aircraft weight increases. That combat effectiveness over time is determined by preserving experienced crews rather than optimizing initial aircraft performance. German fighters adopted armor protection progressively through the war, initially resisting the weight penalty, finally accepting it as combat experience matched American lessons. The Hellcat was designed from the beginning with armor as primary requirement. Pilot protection prioritized over performance optimization. The instrument panel is comprehensive, clearly organized, reflecting American philosophy of providing pilots with complete information to manage complex systems. Engine instruments for the R2800 include manifold pressure, RPM, fuel pressure, oil temperature, cylinder head temperature, carburetor air temperature. Flight instruments include airspeed indicator, altimeter, rate of climb indicator, artificial horizon, directional gyro, turn and bank indicator. Tactical instruments include fuel quantity gauges for internal and external tanks, ammunition counters for each gun, hydraulic pressure gauge, oxygen pressure gauge. The instrumentation is far more comprehensive than typical German fighters, reflecting American emphasis on system monitoring and allowing pilots to operate complex aircraft safely, even with moderate training. German fighters have simpler instrument panels, relying more on pilot skill and experience to manage systems without detailed information feedback. The throttle quadrant includes separate controls for throttle, propeller pitch, mixture, supercharger stage, cowl flaps. All the parameters a pilot must manage to optimize engine performance for different flight conditions. The complexity is significant, but the layout is logical. Controls positioned where they are easily reached, operation becoming routine with practice. Worcester notes the armament installation with particular interest. The Hellcat carries 6 .50 caliber Browning M2 machine guns, 3 mounted in each wing with 400 rounds per gun, total of 2,400 rounds. The concentration of fire is substantial, 6 guns converging at 400 yards, creating a cone of destruction that few aircraft can survive. The rate of fire is approximately 800 rounds per minute per gun, meaning a 2-second burst delivers 160 rounds of .50 caliber ammunition. German fighters typically carry 2 to 4 guns with total ammunition of 600 to 1,000 rounds, less firepower and less ammunition capacity than the Hellcat. The American philosophy is to carry heavy armament and substantial ammunition, allowing pilots to engage multiple targets per mission and to use longer bursts to ensure kills, rather than conserving ammunition carefully. German fighters increasingly conserve ammunition due to shortages, pilots training to fire very brief bursts, accepting reduced kill probability to extend time before requiring rearmament. The Hellcat's ammunition capacity reflects industrial capacity to produce ammunition in quantities that allow profligate use rather than careful conservation. September 21, 1944. Weather has cleared sufficiently for flight testing. Ceiling 10,000 feet with scattered clouds, visibility 15 kilometers. Wind from west at 20 knots, conditions adequate for performance evaluation if not ideal. Boer will fly the Hellcat first, conducting basic handling and performance testing, establishing baseline data that engineers can analyze. Ground crew prepare the aircraft. Unfolding the wings manually using hydraulic hand pumps after electrical power proved insufficient. The process taking 20 minutes and requiring 4 men, demonstrating one disadvantage of folding wings compared to fixed wings that require no preparation. Once the wings are unfolded and locked in flight position, the Hellcat looks significantly larger, the 42-foot wingspan giving proper proportions to the deep fuselage and massive engine. Boer performs external pre-flight inspection, checking control surfaces, examining the repaired structure, verifying the propeller attachment, confirming fuel tanks are full. The Hellcat carries 250 gallons of internal fuel, plus provisions for 2 150-gallon external drop tanks on underwing pylons. Total fuel capacity of 550 gallons, allowing extended range that German fighters cannot match. For this test flight, only internal fuel is loaded, eliminating the drag and weight of external tanks. Boer climbs into the cockpit, straps in using the American-style shoulder harness that is more comprehensive than German harness systems. Familiarizes himself with controls and instruments using reference cards prepared by mechanics who translated the captured flight manual. The startup procedure is straightforward. Battery on. Fuel boost pump on, mixture rich, propeller full forward. Supercharger low stage, cowl flaps open, throttle cracked open 1 inch, magnetos on, engage starter. The R2800 cranks slowly, the massive pistons compressing air in 18 cylinders, then catches with a deep roar that shakes the airframe. The radial engine settles into rough idle at 1,000 RPM, vibrating noticeably, 18 individual exhaust flames visible around the cowling creating slight haze. Boer monitors gauges as the engine warms. Oil pressure climbing to 70 psi, cylinder head temperature rising steadily, all indications normal. He tests magnetos, switching from both to left, checking RPM drop, acceptable 50 RPM drop. Switch to right magneto, same drop, back to both. He cycles the propeller pitch, watching RPM change as blade angle adjusts. Everything functions normally. He releases parking brake, advances throttle slightly, and the Hellcat rolls forward. The ground handling is good, the wide-track landing gear providing stable taxi, the tail wheel providing adequate directional control though requiring significant rudder input. At the runway threshold he performs pre-takeoff checks, mixture rich, propeller full forward, supercharger low stage, cowl flaps open, fuel on main tank, magnetos both, flight controls free and correct, trim set for takeoff. He advances throttle to full power. The R2800 roars, 2,000 horsepower driving the 4-bladed propeller. The Hellcat accelerating down the concrete runway. The acceleration is good, less violent than the lightweight BF-109 but faster than the heavy FW-190. At 80 miles per hour the tail lifts, improving forward visibility. At 110 miles per hour Boer rotates gently and the Hellcat lifts off, climbing away with solid authority. He retracts landing gear, the wheels folding inward into the wings with hydraulic smoothness. He retracts flaps, reduces power to climb setting, and the Hellcat climbs at 2,700 feet per minute at sea level. Very respectable climb rate for a fighter weighing 12,700 pounds fully loaded. The handling during climb is pleasant, controls responsive but not overly sensitive. The aircraft stable and requiring minimal trim adjustments. Boer climbs through 10,000 feet, 15,000 feet, noting that climb rate decreases gradually as altitude increases. Standard behavior but less pronounced than single-stage supercharged fighters, where climb rate drops sharply above critical altitude. At 20,000 feet he levels off, the altitude where the Hellcat reportedly achieves maximum speed, the altitude where German engineers need accurate performance data to compare against German fighters. He allows speed to stabilize at cruise power, 2,000 RPM and 36 inches manifold pressure, achieving 320 miles per hour. Then he advances throttle to military power, 2,600 RPM and 45 inches manifold pressure. Standard combat power that can be sustained indefinitely without damaging the engine. The Hellcat accelerates smoothly, 340 miles per hour, 360, 375. At 380 miles per hour indicated airspeed, the acceleration stops. The Hellcat, settling into level flight at a speed that Boer finds remarkable for a fighter this heavy, carrying all the weight penalties of carrier operations. Boer verifies the airspeed indication is accurate by timing how long it takes to cover known distance between landmarks visible through gaps in clouds. The calculation confirms indicated airspeed is accurate within measurement precision. He is actually flying 380 miles per hour at 20,500 feet in a carrier fighter designed to operate from ships. A fighter carrying folding wings and arresting gear and reinforced structure. A fighter burdened with 800 pounds of equipment that land-based fighters do not carry. He knows from his extensive experience evaluating captured aircraft and flying German fighters that 380 miles per hour at 20,000 feet is competitive with or superior to most German fighters at that specific altitude. The Bf-109 G6, Germany's standard fighter in late 1944, achieves maximum speed of 387 miles per hour at 22,600 feet. Its critical altitude where the supercharger provides optimal boost. At 20,000 feet, where the supercharger is not quite at optimal efficiency, the Bf-109 G6 achieves approximately 375 miles per hour, slower than the Hellcat. The FW-190A8 achieves maximum speed of 408 miles per hour at 20,600 feet, faster than the Hellcat by about 25 miles per hour, but only when flying clean without external stores, without drop tanks, without underwing racks, in combat configuration carrying external fuel tank or bombs. The FW-198 speed at 20,000 feet drops to approximately 380 miles per hour, equal to the Hellcat. The implications are stark and disturbing. The Americans have built a carrier fighter, a naval aircraft designed to operate from ships with all the weight and complexity that entails. That achieves performance equal to or better than German land-based fighters optimized for minimum weight and maximum performance. The engineering to achieve this is sophisticated. The industrial capacity to build it in quantity is formidable. And the philosophical difference from German approach is profound. German engineers obsess over weight reduction, removing every unnecessary component, using lightest possible structure, accepting reduced safety margins to minimize weight. American engineers accept weight as necessary cost of achieving other objectives: carrier compatibility, pilot protection, heavy armament, long range, and overcome weight penalties through brute engineering, massive engines, sophisticated supercharging, aerodynamic refinement. The American approach requires greater industrial capacity, more sophisticated manufacturing, better materials, but produces aircraft that work well in operational conditions rather than achieving theoretical performance that degrades rapidly under combat stress or field conditions. Boer conducts additional performance testing to characterize the Hellcat's capabilities across the flight envelope. He performs turns at various speeds and bank angles, discovering that turn performance is adequate but not exceptional. The heavy wing loading and substantial weight limiting sustained turn rate to approximately 18 degrees per second at optimum speed, compared to 22 degrees per second for the Bf-109G. In a turning fight, the German fighter would gain angular advantage within 2 to 3 turns. But Boer notes that the Hellcat's heavy construction makes it stable at high speeds. Controls remaining responsive and effective at speeds where lighter fighters experience controls stiffening and buffeting. At 400 miles per hour indicated, the Hellcat's ailerons still respond crisply. The aircraft rolls predictably, the controls remain harmonious. The Bf-109G at 400 miles per hour experiences severe control stiffening. Ailerons becoming nearly immovable, rolls becoming very slow. The Hellcat's high-speed handling provides tactical advantages in boom and zoom fighting where high speeds are maintained throughout engagement. He tests dive performance, an important characteristic for naval fighters that often attack ground targets or ships using diving attacks. He rolls inverted, pulls through into vertical dive, allows speed to build. At 25,000 feet, he enters the dive at 300 miles per hour. At 20,000 feet, speed is 380 miles per hour. At 15,000 feet, 440 miles per hour. At 10,000 feet, 500 miles per hour indicated. The Hellcat remains stable throughout. No buffeting, no flutter, controls remaining effective if heavy. At 5,000 feet, he begins recovery, pulling steadily. The heavy structure absorbing gi loads without complaint. Leveling at 2,000 feet after using 3,000 feet for recovery. The dive performance is excellent, better than most German fighters, demonstrating that the heavy structure provides advantages in high-speed regimes where lighter fighters encounter aerodynamic problems. He conducts one final test that Worcester specifically requested: sustained high-power operations to determine whether the Hellcat can maintain combat performance through extended engagements or whether it suffers degradation like many fighters that overheat after sustained full-power use. He climbs to 20,000 feet, accelerates to military power 380 miles per hour, and maintains this power setting for 20 minutes while performing combat maneuvers. Turns, climbs, dives, acceleration, everything that simulates actual combat operations. After 20 minutes of sustained military power, the engine temperatures remain well within normal ranges. Cylinder head temperature at 240 degrees Celsius. Oil temperature at 85 degrees Celsius, both comfortably below redline limits. The cooling system is adequate to prevent overheating during extended combat. The engine is designed for sustained high-power operations without degradation. This sustained performance capability is a key American advantage, allowing their fighters to maintain combat effectiveness through extended engagements where German fighters must reduce power to prevent overheating. After 2.5 hours of comprehensive flight testing, Bauer returns to Vernes. The landing is straightforward. The approach speed 115 miles per hour. Touchdown gentle despite the heavy weight. The robust landing gear absorbing impact without drama. He taxis back to the revetment, shuts down the R2800, and sits in the cockpit for several minutes processing what he experienced. The Hellcat is not a spectacular fighter in any single performance category. It does not turn like a Bf-109, does not accelerate like a FW-190, does not climb like a Spitfire, but it is competitive in every category, excellent in high-speed handling and dive performance, and most significantly, it sustains performance through extended operations without degradation. The engineering is mature, sophisticated, reflecting years of development and testing. The construction quality is superb, reflecting industrial standards German aviation can no longer match. Most disturbingly, this is a carrier fighter, a naval aircraft accepting all the weight penalties of shipboard operations, yet achieving performance that land-based German fighters struggle to match. If American naval fighters are this good, Bohr wonders, how good are their premier land-based fighters like the P-51 and P-47? He climbs down, his expression grim. Worster flies next, bringing engineering perspective to the evaluation. He is not a test pilot. His flying skills are adequate but not exceptional, but he understands aircraft systems and performance theory better than most pilots. He takes off, climbs to 20,000 feet, and conducts methodical performance testing, measuring every parameter precisely. He confirms Bohr's speed findings, 380 miles per hour at 20,500 feet at military power. He measures fuel consumption at various power settings, discovering that at military power, the R2800 consumes approximately 150 gallons per hour, giving the Hellcat approximately 90 minutes endurance on internal fuel at combat power, adequate for carrier combat air patrol missions or escort missions. He measures climb performance at various altitudes, documenting that the two-stage supercharger maintains good climb rate to 25,000 feet, above which performance degrades as even the two-stage system can no longer maintain adequate boost pressure. He performs the test that interests him most as an engineer, determining exactly how the two-stage supercharger maintains power at altitude. The R2800's supercharger system uses two centrifugal compressor stages with hydraulic clutches allowing either low or high-speed operation of each stage, creating 4 possible combinations but typically operating in 2 modes: low gear for low to medium altitude, high gear for high altitude. At 20,000 feet, both stages operate in high gear, the first stage compressing air to intermediate pressure, passing it through an intercooler that reduces temperature and increases density. Then the second stage compressing further to final manifold pressure. The intercooler is key, preventing the compressed air from becoming so hot that it loses density and causes detonation. German single-stage supercharged engines compress air at once, cannot achieve the same final pressures as two-stage systems, and have lower critical altitudes above which power drops rapidly. Worster calculates that the R2800 at 20,000 feet is producing approximately 1,850 horsepower, only 8% less than its sea-level power, while the BMW 801D at the same altitude produces approximately 1,300 horsepower, 24% less than sea-level power. The difference in power retention at altitude explains the Hellcat's competitive speed despite heavier weight. Worster lands after 3 hours of methodical testing, his engineering notebook filled with performance data, thermodynamic calculations, systems analysis. His conclusion is unambiguous: the Hellcat achieves its altitude performance through superior supercharging, technology that German aviation has attempted to develop but failed to implement successfully in production engines. Germany has experimental two-stage supercharged engines, the DB605L with two-stage system, the BMW 801F with turbo supercharging, but neither reached reliable production by September 1944. The technical challenges, manufacturing difficulties, material shortages, all combined to prevent German two-stage systems from becoming operational. American aviation solved these problems years earlier, benefited from British collaboration sharing Rolls-Royce supercharger technology, invested resources in development and testing that Germany could not match, and by 1944 operates multiple fighter types with two-stage superchargers as standard equipment. The technological gap in supercharger development is one of the decisive factors in the air war, allowing Allied fighters to dominate at altitudes where German fighters are weakest. Zeidel, the supercharger specialist, examines the R2800 supercharger installation in detail over 2 days, disassembling components, measuring dimensions, photographing everything, attempting to understand exactly how American engineers achieved reliable two-stage operation. His analysis identifies several innovations that German designs lack or implement less effectively. The intercooler uses finned tubing with optimized geometry, maximizing heat transfer while minimizing pressure drop, achieving better cooling efficiency than German intercoolers. The hydraulic clutch system for changing supercharger speeds is sophisticated and reliable, using pressure-actuated clutches that engage smoothly, while German systems using mechanical clutches are less reliable and prone to failure. The supercharger drive gearing is precision manufactured with tight tolerances, reducing friction losses and improving efficiency. The bearings supporting the supercharger shafts are high-quality roller bearings, allowing sustained high-speed operation without excessive wear. Every component shows engineering refinement and manufacturing quality that German aviation struggles to match in late 1944, when production pressure demands simplified designs and relaxed tolerances. Zeidel's report concludes that replicating the ART 2800's supercharger system in German engines would require 18 to 24 months of development, even if materials and manufacturing capacity were available, which they are not. The precision manufacturing required for supercharger components exceeds current German capabilities, given Allied bombing damage to machine tool factories and skilled labor shortages. The materials required high-temperature alloys for turbine components. Aluminum alloys for impellers and housings are in short supply due to Allied interdiction of resource supply lines. Even if development were successful, production of two-stage supercharged engines would be slower and more expensive than current single-stage engines, reducing output at a time when quantity is desperately needed. Zeidel's conclusion is that Germany cannot match American supercharger technology within the time frame that matters for the war's outcome, that the technological gap will persist until war's end, and that this gap gives Allied fighters decisive advantages at medium to high altitudes where much of the air combat occurs. Hoffman, the structural engineer, examines how the Hellcat structure achieves strength adequate for carrier operations without becoming prohibitively heavy. He discovers that American engineers used several techniques German designers either overlooked or considered too expensive for production. The fuselage uses geodetic construction in critical areas, multiple small structural members creating three-dimensional framework distributing loads efficiently, similar to British aircraft like the Wellington bomber but refined for fighter application. The wing structure uses thick skins in closely spaced ribs, creating a semi-monocoque structure that is very stiff and strong, distributing landing loads throughout large sections of wing rather than concentrating loads at attachment points. The landing gear attachment uses massive steel fittings heat-treated to very high strength, distributing loads to multiple wing ribs and fuselage frames. The resting hook mount is a structural masterpiece. Loads from arrested landings distributed through heavy steel framework extending forward into the fuselage, preventing concentration that would crack structure. Hoffman calculates that the Hellcat structure is approximately 30% heavier than an equivalent German fighter structure designed only for land operations, but achieves approximately 3 times the strength in critical load cases like carrier landings. The efficiency strength achieved per pound of structure is actually better than typical German practice, suggesting American stress analysis and structural optimization are more sophisticated. Hoffman notes that the Hellcat structure uses extensive spot welding rather than riveting in secondary structure, a manufacturing technique that reduces labor and improves strength by eliminating rivet holes that weaken structure. German aircraft use riveting almost exclusively, spot welding considered too expensive and requiring equipment most factories lack. The structural analysis confirms that American aviation has advantages in structural engineering knowledge, in manufacturing technology, and in willingness to accept weight to achieve other objectives like pilot protection and operational reliability. September 25, 1944. The evaluation team compiles findings into technical report for distribution to German fighter development organizations, Luftwaffe operational commands, and Ministry of Aviation for policy guidance. Worster writes the core engineering assessment, his analysis systematic and comprehensive, his conclusions carefully worded but unambiguous about implications. The Grumman F6F Hellcat, he begins, represents the state of American naval fighter development in mid-1944. A carrier-based aircraft designed for shipboard operations, accepting all the weight penalties such operations require. Folding wings adding 250 pounds, reinforced landing gear adding 500 pounds, arresting gear adding 100 pounds, strengthened structure adding 400 pounds, total carrier-specific weight penalty approximately 1,250 pounds compared to equivalent land-based fighter. Despite these penalties, the Hellcat achieves maximum speed of 380 miles per hour at 20,500 feet at military power sustainable indefinitely, competitive with or superior to German fighters at the same altitude, including the Bf-109G6, which achieves approximately 375 miles per hour at 20,000 feet, and the FW-190A8, which achieves approximately 380 miles per hour at 20,000 feet in combat configuration, with external stores. The Hellcat's performance, Worcester continues, is achieved through three primary engineering approaches. First, massive engine power. The Pratt & Whitney R2800 produces 2,000 horsepower, 300 to 400 horsepower more than German radial engines, overcoming weight disadvantages through brute force. Second, sophisticated supercharging. The two-stage, two-speed supercharger maintains power at altitude far better than German single-stage systems, producing 1,850 horsepower at 20,000 feet compared to 1,300 horsepower for the BMW 801D at the same altitude. Third, aerodynamic refinement. Careful attention to drag reduction through streamlining, surface quality, cooling system design, extracting maximum performance from available power. The combination allows the Hellcat to match German land-based fighter performance despite 800 to 1,000 pounds of additional weight for naval features. The implications, Worcester writes with careful diplomatic phrasing, are significant for understanding the trajectory of fighter development and the relative capabilities of German and Allied aviation industries. If American naval aviation can field carrier fighters with performance matching German land-based fighters, this demonstrates either that American engineering has overcome weight penalties through superior technology, or that German engineering has failed to optimize land-based fighter designs adequately, or both. The two-stage supercharger technology is clearly superior to German single-stage systems, allowing sustained power at altitudes where German fighters lose effectiveness. The structural engineering is sophisticated, achieving high strength efficiently. The manufacturing quality is excellent, showing attention to detail and quality control that German production increasingly cannot maintain. Most concerning, the Hellcat is produced in large numbers, over 12,000 built by September 1944, according to intelligence estimates, demonstrating industrial capacity to manufacture complex aircraft at scale while maintaining quality. German fighter production in 1944 totals approximately 25,000 aircraft, all types. Impressive quantity, but with declining quality as production pressure increases and resources diminish. Worcester recommends that German fighter development prioritize two-stage supercharger development, even though timeframes make affecting current war unlikely, because future aviation will require altitude capability that single-stage systems cannot provide. He recommends structural engineering studies to understand how American designs achieve high-efficiency learning techniques that might improve German designs. He recommends manufacturing studies to understand how American factories maintain quality at high production rates, identifying practices German industry might adopt. He recommends honest assessment of German fighter performance compared to Allied aircraft, without propaganda distortions, so design decisions can be based on reality rather than wishful thinking. Finally, he recommends acknowledging that American industrial capacity has reached the point where they can afford to build heavy, complex, robust aircraft in quantities that overwhelm any advantages German lightweight designs might have, and that Germany's strategic situation requires accepting this reality and planning accordingly. The report, 98 pages including technical appendices with performance data, structural analysis, and supercharger diagrams, is dated September 27, 1944, classified Geheim Secret, and distributed through Ministry of Aviation channels. Reaches various recipients through October, landing on desks at Messerschmitt, Focke-Wulf, Daimler-Benz, BMW, and Luftwaffe High Command. Reactions vary but follow predictable patterns. Engineers acknowledge the technical accuracy, understanding that American supercharger development has outpaced German efforts, that American manufacturing quality exceeds German capabilities in late war, that the technological gaps documented in the report are real and significant. Production managers express frustration that reports documenting Allied advantages provide no actionable solutions given resource constraints and time pressures. Luftwaffe commanders incorporate the findings into tactical assessments, but note that operational reality already reflects what the report documents. Allied fighters are superior in most regimes. German pilots must accept unfavorable combat conditions or abandon missions. Ministry officials file the report in archives, recognizing its accuracy but seeing no policy implications since Germany cannot significantly alter fighter development or production priorities in the war's final months. The evaluation changes nothing because Germany in September 1944 lacks resources, time, and strategic position to respond to technical intelligence, regardless of accuracy. The report documents the problem clearly but offers no solutions that are achievable within relevant timeframes. German fighters will continue production using existing designs with incremental improvements. German engines will continue using single-stage superchargers because two-stage systems cannot be developed and produced quickly enough. German manufacturing will continue declining in quality as Allied bombing destroys factories and skilled workers are killed or drafted. The air war will continue with increasingly unfavorable outcomes for Germany until final collapse in May 1945. The Hellcat evaluation, like dozens of other captured aircraft evaluations, becomes historical footnote documenting German awareness of their technological disadvantages without being able to affect strategic outcomes. Post-war, the evaluation participants reflect on what the Hellcat revealed about American industrial philosophy and German engineering failures. Worcester survives, works in post-war German aviation industry contributing to development of civilian aircraft, retires in 1972, dies in 1989. In a 1983 interview for Aviation History Journal, he describes the Hellcat evaluation as watershed moment in understanding how completely German aviation had been surpassed by American development. The Hellcat was a carrier fighter, he recalls. Naval aircraft accepting huge weight penalties, yet matching or exceeding German land-based fighters optimized for minimum weight. The engineering to achieve this was impressive. The industrial capacity to build 12,000 of them was formidable, and the philosophical difference from German approach was instructive. Germans obsessed over saving grams, he says. Americans accepted kilograms to achieve operational objectives. The American approach worked better because robustness and reliability in field conditions matter more than theoretical maximum performance achievable under perfect conditions. German fighters were optimized for peacetime test conditions, he says. American fighters were optimized for combat conditions with undertrained pilots. Minimal maintenance, damage from ground fire and enemy fighters, all the realities of operational aviation. Boer survives with 220 victories, becomes one of the highest scoring aces to survive the entire war, works in various post-war capacities, dies in 1993. In 1990 memoir, he reflects on how many captured Allied aircraft he evaluated during the war, over 30 different types, and how each successive evaluation revealed growing Allied advantages. The Hellcat, he writes, was particularly significant because it demonstrated that American engineering could achieve excellent performance even in aircraft burdened with carrier requirements. If their naval fighters were this good, he writes, their premier land-based fighters like the P-51 and P-47 were obviously even better, and German fighters had no hope of competing. He describes feeling demoralized during the Hellcat evaluation, understanding that the war was lost not because German pilots lacked skill or courage, but because German aircraft were increasingly obsolete, designed with philosophy that prioritized wrong characteristics, built by industry that could not match Allied quality or quantity. The F6F Hellcat served through war's end and beyond, over 12,500 built total, achieving devastating success in Pacific combat against Japanese aviation with kill ratios exceeding 19-1. One of the most successful fighters of the war, the Hellcat demonstrated that carrier fighters could achieve performance competitive with land-based fighters through sophisticated engineering and powerful engines, validating American design philosophy that accepted weight and complexity to achieve operational effectiveness. The two-stage supercharger that German engineers analyzed in the captured aircraft became standard on most American high-performance aircraft, providing altitude capability that German single-stage systems could not match. The structural techniques that allowed the Hellcat to survive carrier operations while maintaining competitive performance influenced post-war carrier aircraft design globally, demonstrating that naval aviation could achieve capabilities previously thought limited to land-based aviation. The broader lesson the Hellcat evaluation offered but that German aviation could not act upon was that sustained performance. Reliability and operational robustness matter more than peak theoretical performance in determining combat effectiveness. German fighters achieved impressive performance numbers on test stands and in carefully controlled evaluation flights, but degraded rapidly under combat conditions when engines overheated, when structures failed under sustained stress, when quality control lapses caused systems to malfunction. American fighters like the Hellcat were designed from the beginning to maintain performance through extended operations, to survive damage and continue functioning, to be maintained by undertrained mechanics with limited tools and field conditions. The engineering philosophy differences reflected industrial capacity differences and operational experience differences. American industry could afford to build heavy, robust aircraft because they had materials and manufacturing capacity to do so. American military aviation had operational experience with large-scale combat operations in primitive conditions, understanding that reliability matters more than maximum performance. German industry increasingly lacked resources to build anything but minimalist designs. German military aviation clung to theoretical performance optimization, even as operational reality demonstrated that theories failed in practice. The Hellcat evaluation revealed that American carrier fighters accepting 800 pounds of weight penalties for naval operations still matched German land-based fighters at 20,000 feet through superior supercharger technology and massive engine power. That 380 miles per hour was achievable in a naval fighter designed for shipboard operations, and that German engineering philosophy prioritizing weight reduction over operational robustness had failed to match American philosophy prioritizing sustained performance and reliability. German engineers understood this after testing the Hellcat, but Germany lacked resources and time to respond. If you want more stories about how engineering philosophy shaped World War II outcomes, subscribe now. We publish these technical deep dives every week. Thanks for watching.